Hello, this is Ali from midas, South Korea. In this video demonstration, we will be discussing how to model a RC deep beam for the concrete crack propagation analysis. We will initiate by modeling the concrete beam and the reinforcements, both of the top and bottom rebars along with the stirrups, defining the material properties, defining the load conditions and the boundary conditions, and setting up the analysis case. And in the end, we will be having a look how to extract the stresses, crack pattern, the status and the propagation phenomena within the reinforced beam, and how to extract the results in the form of load deflection curve. So let's have a look at the geometry of the beam. The beam is 8.75 centimeter wide, 15 centimeter high, 120 centimeter long. The concrete cover will be 1 centimeter, and we have some shear reinforcements as the information is provided here, with a spacing of 15 centimeter in the middle and 14 centimeters at both sides. The related function we will be using in the program for the geometric modeling will be some features solid and using a box, and drawing the reinforcements and the stirrups using some 2D rectangles and 3D lines, and then we will be performing some transforming actions to complete our model, and then we will be completing the meshing, and we will be checking on these tools in our video demonstration. The properties associated with concrete and steel are listed here. The main thing to be discussed here is the total strain crack model, which is mainly considered to simulate the crack propagation. The basic idea or the major concepts to be understood are lateral crack effect, confinement effect, some properties regarding the tension stiffening and tension softening, and some compression hardening and softening curve. And in the reinforcement, steel reinforcement, we have different properties for the bottom and top rebars, and von Mises model will be used to simulate the steel effect, and the idea of embedded reinforcement bar tie will be used to model the reinforcement. So when we will be discussing about the total strain crack model, so generally the non-linear material behavior of concrete is modeled with the total strain crack model, and the reinforcing steel is introduced in FEA using the embedded reinforcement formulation, which actually implies a perfect bond between steel and concrete. And in other words, we can say that if there is no nodal connectivity within the concrete and the steel reinforcement provided, because the material are different, so in certain programs or in certain cases there is a problem of convergence, but by using a embedded type reinforcement element, the nodal connectivity will be having no problem. It will act as a complete bond between the reinforcement and the surrounding concrete area. So the constitutive model involves the concept of fixed and rotating crack models. The stress and strain relationship are defined by these. The fixed crack model is basically about that if the crack plane we want to set our crack plane to be fixed, or it has to be rotating. So generally it is on the user's choice, depending on the purpose of a simulation or what are the real conditions to be simulated. But as the information regarding the program should be known, fixed crack model is mainly used in the 2D type analysis. For example, if we are considering a 2D beam, then we can go for a fixed crack model, and if we are considering a 3D beam, then the choice can be made depending on the expected crack distribution or the crack planes. Then we have two methods, tangent and a secant method. The next thing is lateral crack effect and confinement effect, and the basic properties: tension function, compression function, and shear function. So these are mainly the inputs which we need to input into the program. Lateral crack effect. So let's discuss it one by one. that how the program considers the compressive behavior or the compression softening and the tension behavior as well. So tensile behavior is something which is controlled by the formation of microcracks. Before discussing further, I would like to show some of the compression model and the tension model provided in the program, and later we will be seeing it in the video demonstration as well. So we can provide the compression model as elastic or constant or Thornfeld, which is particularly being used in this current case study, linear, multilinear, etc. And the tension model for the tension stiffening and softening effect can be defined as follows, listed here. And object will be used here in our case, and the models for the shear retention, either the user wants to provide some reduction in the elastic modulus, that can be provided. So then we will be going through some analysis. So let's discuss about the tensile and the compressive behavior. So as I have said that we will be using Thornfeld for compression model and Hodgick for tension model. So the tensile behavior, concrete tensile behavior, is something which is controlled by the formation of microcracks, and if the tensile stress reaches a certain limit, for example in our case the tensile the force at the yield will be 3 Newton per millimeter square. So if the tensile stresses reaches a certain limit, which is probably this, which we will be providing in this model, the additional deformation will localize within the region which will be called as a fracture process zone. So after the tensile limit is reached, the stress in that fracture zone decreases as the strain increases. So when the tensile stress approaches 0, a macro crack will be formed in the fracture zone. So this phenomena is basically known as a tension softening, and we can consider it using the models presented here. So as I've said, we will be using Hodgick here, so that function will be defined here in this section. Then the compressive behavior. So the compressive behavior is assumed to be linearly elastic up to 30% of the uniaxial strength Fc prime. In our case it will be 37.5, I guess. Yeah, here it is. So that function will be defined here. So how does it work? That up to 30% it will stand as a linear elastic. So above that level we can observe the non-linearity, and if the simulation is okay, so we can check such kind of behavior in our final load and deflection curve as well. But when the concrete is in tension and it is subjected to compression parallel to the crack direction, the compressive strength and stiffness will be reduced, and this concept is being presented by Vecchio and Collins, and that concept is incorporated in Midas FEA, total strain crack model. And if the concrete on the contrary, if the concrete is subjected to biaxial or compressive stresses, the compressive strength will increase due to the effect of confinement. So that confinement effect can be taken into account using Selby and VQ model. So if we will talk simply, so we can say that if the crack in the crack concrete, if the tensile strains are perpendicular to the compressive direction, the principal compressive direction, so it will reduce the compressive strength. So this phenomena of the reduction in the compressive strength due to the tensile strains is called as compression softening, and we can provide some shear retention functions here too. We will be looking further into the main demonstration. So this was just roughly an idea about the basic concept of the crack model, strain crack model we are using in the program. So moving on, the load and the boundary conditions, how it can be applied. Well, simulating this kind of situation, there are lots of ways to model and define the loading conditions. So in this particular case, I would be defining the load as displacement control, and it is on the user's choice that if they want to apply the prescribed displacement at once with different incrementation, or they can make as stages that the load will be applied sequentially in increments like as -1, -2, -3, -4. And after defining the load and boundary conditions, we would be setting up the analysis control and check all of the options which are related to the cracking, so that we can have our output. If you forget to check these on, we will not be able to see the results in the post process mode. So one thing to be noted is rigid link. The use of rigid link is quite efficient, as the model is 3D, so we can use a rigid link approach to define a master and slave nodes, so that the load will be applied to the one node only, and it would be sequentially applied to the accordingly applied to the rest of the nodes as well, and the fixed supports will be applied. So in the analysis case, the case will be of non-linear static, and we'll be checking on certain options which will by default consider all of the meshing elements and boundary conditions. Only we have to activate the load. We will get to see these things in the demonstration. And in the nonlinear analysis control, we have to select our iteration scheme. So midas FEA provides lots of 4 different iteration method: initial stiffness, Newton-Raphson, modified Newton-Raphson, arc length method. So it is again based on the concept. It's on the user choice what to use, but for this specific purpose, we will be using, one can use Newton-Raphson to be efficient, but if this kind of crack propagation is being done on certain case like the load is of cyclic type, then the arc length method would be more appropriate, and we can provide our convergence criteria, and we can check on if the analysis terminates. So if the analysis diverges, we need to terminate it, so that we can see that where the rupture is end, or the analysis is done, beyond which step it cannot proceed further. And these are the results we will be getting in the end: the stresses, reinforcement stresses, 3D stresses, crack pattern, crack status, and some result extraction like this. So let's open the program. Yeah, so here we have opened our program. So I'll be creating a new file, click on new. So this is our basic analysis control. The analysis type is 3D, and we can set our unit system in this dialog box. So I'll keep it as default because we will be changing it sequentially. Okay, let's start our modeling. I'll be changing the units to centimeter because the principal dimensions are in centimeter of the beam. So first we will initiate by creating the concrete beam. So we can click on the tab here, solid, and the icon box. We need to specify the origin, the corner, the length in the x direction, which is 120, the width, which is 8.75, height as 15, and we are defining the dimensions with respect to global coordinate system. Here you can name it. So before clicking apply, it is more convenient to click on preview so that we can have a look either the command has executed well. So it is okay, we can click apply. So after this we will be creating our reinforcements, which can be done by clicking on curve and the icon line 3D, and the same feature can be accessed by the menu bar here, geometry, curve, create 3D, line 3D. So as I have mentioned in my discussion earlier, that the concrete cover will be 1 by 1 centimeter. So we will start with 1 by 1. Apply, and at the length of 120 centimeter, click apply. So we can see here in the tree menu that one solid and one curve has been generated. So as it is difficult for us to see the reinforcement or the edge line or the curve we have created, so we can change our display mode of a certain geometry by right clicking on the name of the section or selecting it on the screen and right click mode wireframe. So if I'll click on the front view, our reinforcement is generated, so I think it's not right, so I will be just creating it again. Zero comma 1-1, apply. Then relative coordinates, in the relative coordinates 120, 0, apply. So if you will see the front view, our reinforcement is being generated with a cover of 1 centimeter. So as we have two reinforcements at the bottom and two reinforcements at the top, so what we can do, we don't need to create it all over again. We can use our transforming features, geometry, transform, translate, or we can click on the icon here under the curve tab. So once you will be clicking on the translate option, this dialog box will appear. First we need to select the object which we need to transform or translate. Select the direction. I would like to translate it in the lateral direction first, and copy. So the cover is 1 centimeter from the other side too, so it would be 6.75. Here click apply. Now both of the reinforcements can be translated up to create the top reinforcements. Select direction, set direction, uniform, copy as 13, apply. So here we can see this geometry for the beam and reinforcements has been created. Now we will create the shear stirrups. So before doing thing, I will just try to emphasize on a point. I am here trying to create a rectangle. So the cover of the shear stirrups are same, but if you can see that I'm not able to get the rectangle in the desired position. So the reason is we have to move the orientation of the location of the work plane. So we have to move our work plane, which can be done by the icon here, move work plane, or simply we can use a short key, Control M. So I want to move my work plane in the global YZ. So by simply clicking it and preview, so as we can see, the work plane has been shifted. Click apply. So now curve, rectangle, defining the first location of the first coordinate. Here you can see it's coming up. So here we have created the basic shape. So now we have to perform again some translating or transforming actions. So simply for your convenience, you can click on this icon, select the rectangle and move it to 1 in the global X direction. Preview apply. So the first shape setup has been created. Now by simply one command or one time selection, we can create all of our stirrups by selecting the direction in as X and copying it as non-uniform copy. So as I have said earlier that there will be reinforcements at 14 centimeter at both sides, both ends of the beam, and at 15 centimeters for 14 centimeters in the middle. Sorry, 14 centimeters at the both ends and 15 centimeters in the middle. So I would be providing the information here like this. So if you preview front view, so you can see the reinforcements or the geometry for the stirrups has been created. So the next step here is to define the material properties, which is under Analysis tab, Material. Click Create. Enter the name of the material. Okay, for the convenience as the units for the material, we will be changing it to millimeter. Now again, Analysis, Material, Create, enter the name, modulus of elasticity as 31,000 Newton per millimeter square, Poisson's ratio 0.16, unit weight as 0.0024. So constitutive model, as we have discussed, total strain crack model, we are assuming the crack model as to be fixed, and the secant stiffness method with the lateral confinement effect and the lateral crack effect as well, and the basic properties. So the basic properties here, if I click on use code, I will explain a bit. And actually before that, I would show you the basic tension softening model, in which we will get to see the terms I would like to explain. So this is the basic modeling, or the model, the constitutive model, or for the tension softening and tension stiffening. So the idea is the same again as I have mentioned earlier, that if the tensile stress will reach the certain tension limit, there will be some formation of micro cracks in the region, some deformation and formation of micro cracks in this region. So this area GF by H is known as the fracture zone area, the fracture energy as well. So for the calculation of this area, we have to provide the information about H, which is basically the crack width, what would be the crack width, and it depends on experience as well, and generally taken as the element size, or the not the mesh size of whole of the model, but the one single element size. And in the literature, the formulation provided to calculate the H value is the square root of the total finite element area. So based on that, we can calculate it and provide our H value here. And for GF is the fracture energy, the amount of energy we require to create a unit crack within the concrete, and the FT would be the tensile strength of the concrete. So this GF value can be also calculated if we have, which is basically can be obtained from some experimental data, but if one does not has experimental value, the code specifies this in terms of what would be the grade of the concrete and the maximum aggregate size, and the properties will be calculated accordingly. But as I'm using here as direct input, so it means I can input my fracture energy or the crack width value as desired. So clicking on the tension function, model type would be tension and the function type will be Hordijik, and the Ft is of concrete is 3 Newton per millimeter square. GF is 0.009735, and the H is I'll be taking here as 25 mm, and this is exactly the same value which I would be keeping for my mesh size as well, and I can name the function same as it is. Click apply. For the compression function, simply change the model type to compression and select as Thorenfeld. Change the name, and the design strength of concrete 37.5, and this is the basic curve for which this model follows, and click apply. So here we can select our tension and compression softening functions. The shear retention can be provided as well as elastic constant multilinear, the beta value. So by default, if it is not selected, it can be taken as elastic. So after defining all these parameters, we can simply click as apply, and please note that the material is isotropic. Then the second thing is defining the material for the bottom rebars. We can select it from the database. So we are going to select our rebar as S460 as per the standards, the European standards. So if you'll click it, the values will come up automatically, and we have to change the constitutive model to von Mises, and the initial yield stress will be 460, and we can change the name as well. Similarly, we can select the material for the top and shear reinforcements as 275. The values are changed as well. So top, changing the initial yield stress to 275. Click OK. So now we have defined the three material properties. Now the next step is to mesh, and when we will be meshing the model, we will be requiring some property which would be associated to the reinforcement separately and the concrete beam. So let's go directly to mesh, map mesh, and solid, which is quite an efficient tool to quickly mesh certain geometries, the geometries of this shape. So we can simply click on the beam, and our element size would be 25, and as the property here is 0, so we need to create it. So when we'll be clicking on this icon, a dialog box will appear, so in which we have to name it and simply associate the material and click OK. The same thing can be done if we will go to analysis and click on property. So here we can see that the property is already being generated. So having providing all the details here selected, click preview. The mesh will be of this sort. Click apply. So here we got the mesh for the beam. So the next step is to create the property for the reinforcement, so that afterwards it can be meshed. So analysis, property, click on this drop down box and click on reinforcement. After clicking, this dialog box will appear. So before we create the reinforcement section, we need to create a bar section property which will actually help the program to detect the kind of reinforcement we are providing, either it is embedded or non-embedded. So in case of embedded feature, we have to create this bar section property. So we have nothing to do extra, we just have to simply mention the name and click apply. Afterwards, bar, click on reinforcement, the material to be bottom rebar, and the dia of each rebar is 6 mm. So the cross-sectional area will be 28.278 mm. Click on reinforcement, click apply. So the same bar section can be used for all of the reinforcements, but just for the convenience and for the clear modeling, I am going to create a separate for the bottom, top and shear rebars, shear stirrups. So the die is the same and we just need to change the material. Click apply, and the last bar section for shear rebar, click apply. The material is same, the name has already came here, and click OK. So we have it all of the properties for the concrete and the reinforcements here. So the next step is to mesh the reinforcement. So for the convenience, what we can do is to hide our beam by right clicking it, hide, or we can simply change the display mode. So hiding is better. You need to click on mesh, auto mesh, mesh along edge. So here we can see select mesh, so we can select the two curves or lines which has to be as bottom rebars. We can enter our division. I'm going to keep it the same, but if it is different, that is no problem, because the embedded type reinforcement element maintains a compatibility even if there is no nodal connectivity. So we have to select the property as bottom rebar and check on reinforcement and click on type, bar and solid. But if we are modeling a plate and the reinforcement in plate, so the section can be changed accordingly. Bottom rebar, I can rename it here, preview, apply. So similarly the same procedure can be followed. We just need to change the name of the properties. Apply. Now it's a time for the stirrups. So I'm going to hide all of the created reinforcements and the geometries as well. Just activating the geometry regarding the shear stirrups. So this will make the selection easy for you. Simply click on displayed, okay, or the short key Control A. Number of divisions will be the same, the property name will be changed. Interval length. Apply. So the meshing for the reinforcement has been done. So let's activate all of the meshes along with the reinforcements by right clicking on the mesh, show all, and hide all of the geometry by right clicking hide all. So as we can see, the reinforcements and the shear stirrups are not visible. So what we can do is, again, we can control our display, or we can make it transparent by clicking on the mesh, the certain mesh, and right click display mode, wireframe, or simply we can make it transparent. So the next step is, let's assign the boundary conditions and the loads. So first we will apply the boundary condition, which is at a distance of 12.5 centimeter from both ends. So let's create the boundary set as fixed, which can be created from here as well, but if you'll enter it here and apply the load, the constraint conditions, it will be applied automatically, it will be created automatically. So we have to create the nodes, we have to select the nodes at the distance of 12.5 centimeter. So as I am moving my cursor and the specific node on which I am placing my cursor, it is highlighting as yellow, and one must be thinking how I can get to know the dimensions. So this can be checked here from the bottom. Whenever I move my cursor, the dimensions change here. So here it is, almost 12.5 selected, and from here as well. One 7.5. Here it is. So I have selected as window. So if you will have some isometric or rotated view, you'll get to see that the nodes at the bottom of the nodes has been selected. So clicking on fixed, all of the degree of freedoms will be constrained. Preview, apply. So the boundary conditions has been created. The next step is to create the load by going into analysis, click load, displacement. So in order to apply displacement, there are different ways, and the same situation can be simulated in different ways. Either we can apply the displacements directly to the nodes by selecting the nodes, or another way of simulating the situation, just to make you familiar with one of the modeling technique, is creating rigid link. So for this approach, we have to create a node by going to mesh, node, create. So if we are not using the rigid link and we are providing the prescribed displacement of same magnitude on the nodes lying in the same plane and the same line, so the results would be the same. So in the end, as I have done some tests and analysis, so I would be showing you the comparison of the results as well. So it is actually on user's choice what is more convenient. So in certain cases, when the master node or there is the same amount of load, and the load to be applied are many in number, and sometimes we require to change it, so it is more convenient to create a rigid link and apply the load on one single node, so that in the future if we want to change it, we can change it with quite ease. So I will select here creating a node between two nodes. So what it will do, and this is what I require, I want to create a node for assigning the rigid link in between, in the center of this dimension, the width. So the load is applied 40 centimeter from both ends. So we can see from down what would be the dimensions. So here it is. I would be selecting the node by clicking it. Here, this is highlighted, and the node opposite to that. And if I click preview, we can see assign green symbol is appeared up here, so my node will be created here in between. So here is my node. So similarly, I can do it on the other side. As this demonstration is more focused to get you familiar with the modeling techniques, but if the geometry is symmetrical on both sides, so we can create the half model and provide the symmetric conditions on the other end. So by this way, the results would be coming are reliable as well, because it would be giving the result on the one side, and by mirror view we can see the results on the other sides as well. So I'm not doing that kind of modeling in this because the intention is to make it more clear and easily understandable. So the next load is on 80 centimeter, so I'll be selecting it from here. Click. Sorry, here it is. Preview, apply. So the two nodes have been created and they came in under the mesh set as manual mesh. So if you wish to change the name, you can simply click it, and in the properties area you can change its name, like link node, enter. So the next step is to create the rigid link by going into mesh, element, create link. So all we need to do is to select the master and the slave nodes. So for the master node I'll be selecting this, and the slave nodes, the 4 nodes lying in the same plane, and we have to create the property for the rigid link. So we have to simply click this icon with the type as rigid body and name is at rigid link. Click OK. It came up here. Click apply. So the link has been created. Similarly for the second node. Okay, so the two nodes for and the two rigid links have been created. So finally we have to apply the displacement. So for certain cases in which we have to simulate crack propagation or the crack propagation analysis, in certain cases the displacement controlled loading phenomena or scheme is much more convenient and reliable. The results we'll be getting are more in detail and realistic. However, if you are doing the load control, so that would not simulate the cracks as quite well. It would the model may not converge, or it would end after the tensile stress has been exceeded. So that is the reason I'm simulating it with respect to the displacement. So load as, name it as prescribed displacement. For ease I'm just hiding the beam or simply activating the elements, show only, the nodes. So we just need to click on both of the nodes, check T3 in the Z direction, 0.5 minus 0.5 centimeter, which is 5 mm, preview, okay. So the model is ready. All we need to do is to set the analysis case and run. So for analysis case, you have to click on analysis case, add. The type would be non-linear, which can be selected here from this drop down box, non-linear static. Make sure to check the crack strain and stresses in the output type, otherwise we will not be able to get the results for the cracking. And in the analysis control, iteration scheme Newton-Raphson, but if it's a cyclic loading, then arc length method would be more preferable. And the number of load steps I would keep as 100, with the maximum number of iterations to be 200. And I would like to check on this because I want my analysis to terminate if there is any certain divergence. So click on all for the initial element and initial boundary condition. BC stands for boundary condition. It means whatever the meshes or the reinforcements and the boundary conditions are provided in this dialog box, they will be by default activated, and we just have to activate our load displacement and click OK. Close. Now I would be running my analysis as analysis solve, or simply this tab analysis, Control 5, or clicking this icon. I would be naming here as demo. Okay. Okay, the analysis has been completed and now we can check our results in the post works. As we can see, there has been lots of incrementation as provided in the loads, and the results can be extracted from the post tab and the on curve diagram can be seen. So let's check the reactions. So here we can see the reaction on the right side in the legend, and if you want to see the reaction with the propagation of the load steps, so it can be seen by clicking on the sensor button and scrolling forward. So the reactions will be changing, and similarly if you wish to see the displacements, 3D element stresses, reinforcements, and crack pattern, it can be checked. So let's check it one by one. And if you want to see the undeformed, deformed, or deformed plus undeformed shape, that can be done from here. And similarly, in case of 3D element stresses, midas provides the stresses as von Mises stresses majorly, and maximum shear stresses, principal stresses as well. And for 3D reinforcement, 1D reinforcement stresses, you have to click it here and we can check it accordingly. So the process is mostly the same by which you can check your results, and as it's a crack propagation analysis, so we wish to see the element status, like which zone of the concrete has entered the plastic state or which one hasn't. So by this one we have to click it here. So I would be just changing a bit of the graphical settings to make it more convenient to visualize, to see the things. Okay, so let's check the element status as plasticity. This is the first step in which I think there is zero load incrementation. So along with the increment in the load steps, we can see the plastic state, the regions where the concrete is entering the plastic region. So it can be seen from the legend too. If the symbol or the sign is by PL, so it means it's plastic, and if it's empty, so it means the section or the concrete area is still in the elastic zone. So, and if you wish to see the crack status, that in which area the crack is fully open or partially open, or it's unloading phase, the crack with the fully unloading, or it's not opened yet, or the portion of it is not cracked yet. So we can check it by clicking on the crack status, and it can be checked like this. As we can see, the bottom area in the middle has partially open and full open and fully open, so partially open and fully open. And if we go a bit towards top, the partial opening, upon unloading, cracks can be seen. And as we will be moving forward in towards the next steps, so it can be seen. So the area which is like this, so it means that it's not cracked yet, but the rest of the section has a mix of partially open upon loading and unloading. And as it is not a cycling load phenomena, so we would be hardly seeing any closed crack. Majorly it will be open or fully open or partially open upon loading or unloading phase. Then if we wish to see the crack pattern, the normal cracks or the shear cracks, the diagonal cracks, it can be seen within this menu. And once again, this icon is quite useful, this feature, to see the propagation or the results. So the normal cracks, and for the shear cracks or the diagonal cracks, so for a more clear understanding of these, as we can see, the diagonal cracks here in this region, And if you wish to understand more about these terminologies, so you can refer to the help file as well, help file, and just go to the post tab, the post tab. So the last but not the least, I mean the most important thing, how to extract results in the form of load deflection curve. So this can be done by going through post, extract results. So we will be checking results for nonlinear load case, selecting all and changing the data type, the data to displacement dz as it was a prescribed displacement loading scheme, and clicking on the node here with the global rectangular coordinate system and summation of the nodes we will be selecting. Then now we have to extract the nodes, the results from these nodes we will be selecting. So as we have applied the displacement on more than one load, so it is recommended to select all of those nodes on which the loads has been applied. So let's check. So here we are. So the displacement was applied on 40 centimeters from the left, so I can get to see the distances from my bottom status bar, and just simply selecting it like this, and we will see the nodes are entered here automatically. So if we click on table, so here it is, we'll get to see the summation of all the displacements in this last row. And similarly, if we wish to see, we want to capture or extract the reactions, so again we have to select it on the nodes on which the supports were defined. So it was defined on a distance of 12.5 centimeter. Yeah, so here it is, we can select it and it is automatically updated, and just by simply clicking table. So here it is, we got the results, the summation of the results Fz, reactions Fz in kilonewtons. Now if you wish to see the curve, there is a simple direct way that we can copy and paste these two results, the tables, in Excel, and we can plot our load deflection curve. I'll just show you which I have already plotted. So I'll be just dragging it onto the screen. So here is it, the load versus deflection curve. So as we can see, the ultimate peak point, or the peak point, is almost 42 kilonewtons, and after that we can notice the tension, softening and stiffening behavior, then some little crack effect in this area, so which gives rise to the strength and the stresses. So by this way we can extract our results. And one of the other thing that why we haven't used a load control scheme, so if we would have used a load control scheme, it would be just giving us the results until the maximum capacity, I mean, of the beam, the tension of softening or stiffening, compression softening phenomena is not that easy to simulate when the load controlled analysis or the loading scheme is built up. So this is the comparison of the load controlled graph and the displacement controlled graph. So I think when we wish to simulate the crack propagation or the cracking within the concrete or any other material, or if it's a masonry structure, so displacement control loading is much more recommended to get the more reliable results. So that was it, and if you wish to have any certain query and there is something which was not easy to understand, or I have not been successful to make it understandable, so you can send us your queries on techsupport@midasit.com. I will repeat it again, techsupport@midasit.com. So you can send us your queries and your requests about a certain special analysis you wish to do. So we'll be pleased to solve or help that. So thank you so much for listening. Take care.